Hello everyone. So this will be the part 2 for ligand field theory. We're going to look at the molecular orbital diagrams that describes the energy, crystal field splitting energy in presence of a sigma donor, pi donor, and pi acceptor ligands in an octahedral complex. The ligands, according to spectrochemical series, ranging from weak field ligands and strong field ligands, and all of them are categorized according to three types of donor and acceptor ligands. So there will be a pi donor category, a sigma donor, and a pi acceptor. Some ligands, they can be a sigma donor as well as a pi donor. Now, these will fall under the pi donor category. The pi donor and pi acceptor ligands will do sigma bonding. Only difference is they have pi electrons occupying the pi orbital, or they have vacant pi orbital that is ready for accepting electrons. The sigma donor ligands will only make sigma bonding. This is because they do not have other electrons occupying the pi energy, the pi state. So before we go deep into the molecular orbital diagram, we will get to know the symmetry of every orbitals. For first row transition metals, the valence shell atomic orbitals are 3d, 4s, and 4p. And if the octahedral complex is considered, octahedral complex will have octahedral symmetry. The s orbital will always have A1G symmetry. The p orbital will always have T1U symmetry, and the p orbital is degenerate. The d orbital will have two types of symmetry, EG and T2G for octahedral. For tetrahedral, the G is silent, so there will be only E and T2, no G. Now, because we are considering examples and molecular orbital diagrams for octahedral complexes, the d orbital is split into EG and T2G. These two are the symmetries of the d orbital. The s orbital symmetry is A1G, and the p orbital symmetry is T1U. Now, if you see a label A1G, that is corresponding to, representing the s orbital. And if you see a T1U label, that is the p orbital. The EG and T2G will be labeling the d orbitals. And in an octahedral complex, there will be 6 ligands. And every ligand will be providing one orbital. So the energy splitting will show 3 different symmetries corresponding to 3 different orbitals, the A1G, T1U, and EG. When combined metal and ligand orbitals, when there's overlapping of metal and ligand orbitals, this will create a 6 bonding molecular orbitals and a 6 anti-bonding molecular orbitals. Let's look at the molecular orbital diagram for an octahedral complex with sigma donor ligands. Before metal ion combine or forming bonds with the ligands. So this is the energy splitting the orbital's energy in the free metal ions, and this is the energy of the ligand group orbital. Now, because there are 6 ligands coordinating to the metal ion, we are going to consider 6 ligand orbitals. And the 6 ligand orbitals is labeled as A1G plus EG plus T1U. There are 3 symmetries in the ligand group orbital. Whereas for the free metal ion, we start with the 3D orbital that comprises of the EG and T2G symmetries. And above that is the 4s orbital, which is labeled as A1G symmetry. And on top of that is 4p orbital, which is labeled as T1U symmetry. When there is coordination, when there is bonding, when there is an overlapping of orbitals, when there is a interaction, when they react, when ligands form reaction with the free metal ion, the A1G, this is a symmetry for s orbital. The T1U is the symmetry for p orbital. These S and P will be split into bonding and anti-bonding. Remember, before the overlapping happened, all of them are in the non-bonding state. When overlapping happen, they will be split into the bonding and anti-bonding energy. The bonding energy is always below the non-bonding, and the anti-bonding is labeled with a star. That is always going to be placed above the non-bonding level. So AG, please remember, A1G is the s orbital, T1U is the symmetry representing the p orbital. Now, the A1G and T1U is split from the ligand orbital and from the metal p and s orbital. So the green color, the green dotted line is representing the p orbital split into bonding and anti-bonding from metal and ligand. While the orange dotted line is the line that is showing the splitting, the separation of the bonding and anti-bonding of s orbital from the free metal ion and the 6 ligands. And then the EG is also split. This EG is derived, the separation of EG is derived from the free metal ion 3D orbital and the ligand group orbital. And that gives the bonding EG level and the anti-bonding EG level. Now please note that this part, A1G and T1U energy level is quite close to each other, and they are far apart from EG because the overlapping between the ligand and the metal s and p orbital is so efficient that it actually separates far away from EG, while the d orbital is not that efficient for the ligand. After that, T2G. Now, in discussing the ligand field theory, by constructing molecular orbital diagram, the T2G and EG is going to be looked at. For the octahedral molecular orbital diagram, with the presence of sigma donor ligands, the T2G is positioned at the same level as the non-bonding level of the d orbital. So the T2G is going to be placed at the barycenter line, at the non-bonding line. If you remember, the crystal field theory discusses that the crystal field splitting energy is between T2G and EG in an octahedral system. The T2G is placed at the bottom and EG at the top. But the crystal field theory does not discuss the splitting, the energy level involved between bonding and non-bonding and anti-bonding. So the ligand field theory is an extension of expanding the explanation by crystal field theory. So the T2G here in a sigma donor ligand, if the octahedral complex is comprises of sigma donor ligands, the T2G will be placed at the same level as the non-bonding of the free metal ion 3D orbital. That energy difference between T2G and EG star is the crystal field stabilization energy. This is the crystal field splitting that we see when we discuss the crystal field theory of an octahedral complex. So the delta O is actually the crystal splitting energy between T2G at non-bonding level with EG at anti-bonding level. Let's look at some example of a complex ion comprises of 6 sigma donor ligands. So for example, we have, this should be hexaimine, okay? Hexaamine ion, hexaamine ferrum 2. Hexaamine ferrum 2. Ferrum in this complex is a ferrum 2 plus. A ferrum 2 plus. That actually makes it a D6 configuration. Ammonia is a neutral ligand. Ammonia is a sigma donor, and ammonia is a strong sigma donor. Ammonia cannot make a pi donor because it has no more electrons occupying the pi state. There's no more unpaired electron that can be donated by the nitrogen of ammonia. So ammonia can only be the sigma donor, and it is a strong sigma donor. A strong sigma donor, but ammonia is also a strong ligand. So filling in every ammonia ligand will contribute 2 electrons. So because there are 6 ammonia ligands, there will be 6 sets. Okay, there will be 6 sets where every of the ligand contributes 2 electrons. While the free iron 2 plus have 6 electrons in its d orbital. Now, how do we fill in the molecular orbital diagram? The ligand electron will fill in the bonding state first, and the T2G EG star will be filled in by the electrons from the 3D orbital. So these electrons from the ligand group will fill in the A1G, T1U. So there are 4 ligands and 6 ligands. So altogether, the 6 ligands occupies the 6 ligands electrons occupying A1G, all 3 T1U, and all 2 EG level. Now, where does the electrons from 3D will go? These electrons from 3D will be occupying the T2G and EG star. Now, because ammonia is a strong ligand, the electron will be occupying the T2G level first. So there will be no electron occupying the EG star. So this is how the molecular orbital diagram for such complex looks like. Let's look at other example. Let's say we have a hexachloro ferrum 2 plus. Again, iron here is an iron 2 plus. So iron 2 plus will have 6 electrons in the d orbital. While chlorine here is coordinating to iron in the form of chloride. So chlorine also contributes 2 electrons each. So because there are 6 ligands, 6 chloride, there will be 6 times 2 electron contribution. So again, ligands will fill in the bonding level, So there are 6 of them. All 6 will occupy all bonding level, A1G, T1U, and EG. So what happened to the electrons in the 3D orbital? These electrons occupying the 3D orbital will be occupying the T2G and EG star. Now, because chlorine is a weak field ligand, it will occupy the T2G and EG right away. So there are 6 of them, right? So that's how it looks like in the presence of a weak sigma donor ligand. Halides like chloride, fluoride, bromide, iodide, they are weak ligands, but they belong to the pi donor. Because they belong to the pi donor ligand, they are not strong sigma donor because they can make pi interactions. So this is why chlorine or halides falls under the weak category for sigma donor. They are weak. Okay, they are weak. But it is best to describe complexes with presence of a pi donor using the molecular orbital diagram for pi donor ligands. Again, ammonia is a strong ligand and also a strong sigma donor ligand. You may want to try this. Water is a weak ligand, but water is a good pi donor ligand. So it makes it a weak sigma donor ligand because water would prefer to make pi donation, pi interaction. There is still sigma bonding, but because it can also make pi interaction, so water falls under the pi donor ligand. But if you are asked to use water as a ligand and construct the molecular orbital diagram by using the sigma donor molecular diagram, you use the sigma donor molecular diagram. The molecular orbital diagram for octahedral complexes with pi donor ligands and pi-acceptor ligands, this will depend on the splitting energy between the d orbitals. Whether the T2G star is going to be way above EG star or whether the EG star is going to be way above the T2G star. In the molecular orbital diagram for octahedral complexes consisting pi donor or pi acceptor ligands, the A1G and T1U energy level is still there. Only that in this discussion, we omit A1G and T1U because we want to focus on the splitting of the D symmetries. Because there are distinctions between models of the pi donor and acceptor ligand when involved complexes with pi bonding, pi interaction. Now, in a pi donor ligand molecular orbital of an octahedral complex, again, the A1G and T1U is omitted here, not because they do not exist, but the screen is not long enough to show that because we want to focus more on the energy splitting of the D symmetries. In a molecular orbital diagram for the pi donor ligand, there will be 2 ligand orbitals involved, the sigma orbital and the pi orbitals of the 6 ligands, where both of them are occupied. The sigma orbitals are occupied, the pi orbitals are also occupied. And the reason the ligand is called a donor, because the ligand has electrons to donate. So that explains why both orbitals, sigma and pi, are occupied. And we also have the D, the free metal ion, the D symmetries, Eg and T2G. Only that in the presence of a pi donor ligand, okay, so the splitting of Eg and Eg star derived from both free metal ion and the sigma orbitals from the ligands. And then there's the T2G splitting. The T2G will be placed not so far below the non-bonding level, while the T2G star will be pushed far away from the non-bonding level. Reference to the 3D orbitals. The Eg, on the other hand, remains below T2G, while the Eg star is at the most above T2G star. This T2G splitting into T2G and T2G star is derived from the d orbital of the free metal ion and also from the occupied pi orbitals of the 6 ligands. So what is the main difference here? In the molecular orbital diagram for sigma donor, the T2G is placed at the same line with the non-bonding level as reference to the 3D orbital. But in the pi donor ligand, the T2G is placed below the non-bonding level as reference to the 3D orbital. Not so far below the non-bonding level, but below the non-bonding level. And again, don't forget the A1G and T1U, bonding and anti-bonding state. They are there, but we just don't focus on them because the main difference here is discussed on the splitting of 3D orbitals. The A1G and T1U remain the same. The delta octahedral that we see in crystal field theory is actually this part. So in crystal field theory, when we draw the crystal field splitting diagram, we always show that in the presence of weak or strong ligands, the splitting will be like this, like this, like this. Now, the splitting, the delta octahedral, is actually a splitting energy between T2G star and EG star. A molecular orbital diagram for octahedral complexes with pi-acceptor ligands shows a little bit different from the pi donor ligands. The difference is in the level of the pi orbital of the ligand. The pi orbital of the ligand is a vacant orbital. From the name pi-acceptor ligand, the ligand must have an empty pi orbital for it to accept electrons. And this is why the pi orbital is vacant. But the sigma orbital is occupied so that bonding can happen with the metal-free ion. The EG, bonding and anti-bonding, is separated. And they are derived from the both free metal ion 3D orbitals and the ligand sigma orbitals. And where does the pi orbital place is placed in the ligand? The sigma orbit, the pi orbital is placed way above the Eg star level. And that will actually separate T2G bonding and T2G star bonding. So the molecular orbital diagram for a pi-acceptor ligand puts T2G star way above Eg star. And this is the crystal field splitting energy. Okay, for a molecular orbital diagram that consists of pi-acceptor ligand. This explains why the pi-acceptor ligand is a strong field ligand, the strongest, because it actually splits the Eg star and T2G way much difference compared to the sigma donor and pi donor. Octahedral complexes consisting pi-acceptor ligands are usually not favored for metal centers with D7, D8, D9, or D10 configurations. So for some complexes, we don't use molecular orbital diagram to explain. We have to go by the 18 electron rules, where they have to obey the 18 electron system in order to find out their stability. Try this, construct a molecular orbital diagram for the following. We have the pi donor, sigma donor, pi donor, pi acceptor. Or you may also use fluorine as one of the examples for weak sigma donor. Try this, try to draw your own molecular orbital diagram on your own, because you are going to need this. You are needed to draw the molecular orbital diagram yourself in the exam. So familiarize with the energy level, familiarize with especially the differences in energy involving d orbital.